Hello guys, welcome back to the channel for another PySpark video. This time we are going to have a quick introduction about PySpark DataFrames. In our previous video we discussed about resilient distributed datasets, RDDs, which is the fundamental data structure in Spark. DataFrames came later on and provided a high-level API where we can write SQL queries, which if you ask me, it's very convenient when you are a data engineer. Every data engineer I know loves SQL. Of course, as we mentioned in our last video, data frames are converted into resilient distributed datasets behind the scenes. And that's why it is useful to know a few things about RDDs before we proceed with data frames. On my mind, I like to think a PySpark data frame like a distributed pandas data frame, since they are very similar in terms of functionality. Both of them remind us of the good old relational tables, right? In this video, I have prepared some basic functions of data frames, which I think are quite useful when you start tampering with PySpark data frames for the first time. Anyhow, let's see some slides first, and then we will jump into the practical examples as always. You know, I like hands-on experience. Everyone goes on and on about theory. I like to keep things practical. This is the history of Spark APIs. We discussed this in our previous video. Let's see the definition of a PySpark data frame. PySpark data frames are distributed collections of data that can run on multiple machines and organize data into named columns. Data frames can pull from external databases, structured files, or existing resilient distributed datasets. These are the main features of a PySpark data frame. It supports SQL queries, which is very important. It can infer the schema from the data. Of course, we can specify the schema ourselves, but it can also infer the schema from the data, which is very convenient sometimes. It implements query optimizations using the Catalyst optimizer for improved performance and efficiency when we run SQL queries on a PySpark data frame. In general, it works well with structured data and it supports Java, Scala, Python, and R. Remember, we said last time that data frames under the hood are converted into RDDs, right? Spark SQL the same. But as you can see, there is an extra layer here, the Catalyst optimizer, that optimizes our complex queries in order to improve their performance. If you want to see how the Catalyst optimizer works, I recommend you check the Databricks documentation. It provides a detailed explanation of how it works behind the scenes. There is a lot of code. The guys in Databricks have done a great job for improving the performance of our queries, so we don't have to do that. As you can see, in general, there is this tree transformation framework that we can split in 4 phases to analyze a logical plan, to resolve references. We have the logical plan optimization, the physical planning, and the code generation to compile parts of the query to Java bytecode. Now, performing these transformations, the optimizer improves the execution times of relational queries and frees the developer from focusing on the semantics of their application instead of its performance. Of course, it's very important to improve the efficiency of our queries, and we can do further optimization, but the Catalyst optimizer already does that, already improves the performance of our queries. Now, of course, we have to use cache and persist and use the right operations that avoid data shuffling across the cluster to make things easier for our queries, but also we have the Catalyst optimizer, which is pretty cool. We are in Databricks now. As you can see, I have already created a notebook with the most common and popular operations that we need as data engineers when we play around with PySpark data frames. We are going to load 2 very small datasets from CSV files, and then we are going to perform some operations. The first example would be about converting an RTT to a data frame. So here we define a resilient distributed dataset. We have a list of tuples with a department and some values. And using the 2df, we convert an RTD into a data frame. We also pass the column names here in the list, and if we run this command, we would see the data frame. Let's see, it's running, and here is our data frame, the department and the value. Pretty simple, right? This is how we convert an RDD to a data frame. If you will want to check the type, you can use type, the built-in type function, and run it and see that this is an actual data frame and not an RDD. The next thing is to read the data from the CSV file. We have the file store here. So the file store, if you click on File and then open DBFS file browser, you will see I have uploaded two CSV files. You can, if you right click, you can see upload here, and this is how I uploaded the files. Pretty simple. At the bottom we have the testdata.csv file and the testdata2.csv. Pretty small data sets. In order to read a CSV from the file store, you need spark.read.format. We have to specify the format. In our case is CSV, and we can pass options like whether we want a header, whether we want to infer the schema, and the delimiter. We can also specify the schema, and we will see about that in a little bit. But we can infer the schema as well, which is pretty cool, right? And dot load, and you provide the location of the CSV file. As you can see, we have brackets at the beginning and at the end. This is instead of using a backslash for line continuation. I think it's more convenient when you use a bracket at the beginning and one bracket at the end. Let's run this command, see what we get. It should load the CSV file, and here is our PySpark data frame. It has the ID column, the age column, and the city. Now there are different ways to display a data frame. First, we have the show command. It displays the data like that, like this is a data frame, right? And we also can use head to get only the first 5 records. We can specify the first records, but here we get a list of rows, actually of tuples, right? And then we can use first to get only the first element, exactly the same, just it returns a row. And also we can use the most popular one, which is the display function. Apparently, you can guess why it's the most popular one. It has the best format here, user interface. And we can also use take to get the first 2 rows of a data frame. So there are multiple ways to see the data in our PySpark data frame, which is pretty cool. Okay, so here we can actually define the data types manually. So instead of using the infer schema true here in the options, what we can do is actually define the data types. How can we do that? We have to import from PySpark SQL types. We have to import struct type, integer type, and string type in this case. So this is how you provide the schema. So we use struct type, and then we add the columns, which we have to define the data type of each column. And here we define whether it could be null or not. So this is nullable, right? Because it's true. And then we have the age, which is integer as well, and the city, which is a string. And everything can be nullable. Here you can see that first of all I used backslashes for line continuation and not the brackets at the beginning and at the end. This is another way, whatever you prefer. And again, we are using spark.read spark.format, and we define the file type, which is a CSV, and we, instead of options like that, like we have up here, options, and we provide the options. We can specify the options one by one by using dot option header true, dot option delimiter, and we also can pass the schema here, right? So the schema is the schema that we defined up here, and instead of inferring the schema. Again, we load the same data, and we can display. Let's run this cell above here, and then let's run this as well. And here is our data frame again, but this time we provided the schema manually. Let's move on to the next example. What's the next example is to create a temporary view and query the data from that view. Now, what the command that does that is actually create or replace temp view, which registers a data frame as a table that you can query using SQL. Lasts, as long. I think here we are missing an S. Lasts as long as the Spark session. This method does not allow you to achieve any performance improvement like cache or persist. So here, remember, we have already loaded above our data frame df underscore with underscore schema, and so here we can use our data frame dot create or replace temporary view, and you provide a name for that view, and then you can use Spark SQL to query the view, which comes in handy. So if we run the cell, and now if we query this view, as you can see, it returns a data frame. Pretty cool, actually, right? Now, why do you need to create a temporary view? Well, if you want to use Spark SQL instead of PySpark functions, for example, here we filter the age column that it has to be greater than 40, and we order by ID, and then we just .show, and this will give us back the results. But let's say we want to perform a complicated query. It could be, a little bit cumbersome to do that using the PySpark functions. So that's why we create a temporary view, and we can write normal SQL queries. Select star from test view where age greater than 40, ordered by ID, and it will give you the same results. It's exactly the same thing. Both are converted into RDDs behind the hood, so you have nothing to worry about. But I think it's more legible, let's say, when you use Spark SQL, especially if you have, a background in traditional data engineering, that most people are pretty good when they use SQL, but not many people know how to use PySpark functions. So here we can also, let's say, we create this data frame, right? We select everything from the view with the workflows ordered by, like that. And we can save that, this data frame here, df underscore temp that we defined up here, the results of this query, we can write it as a table, right here, save as table. This is going to run now, and it's going to save it as a table that we can query later on. Give it a second. Now in our Hive default warehouse location, if you go into OpenDBFS file browser and you click on the users, you will see your user, and then you will see Hive, and then you will see warehouse, and then you will see demo, and here we have the data, right? So in our Hive warehouse directory, and we can just use Spark SQL to run the query from and select from the table. It's pretty cool, actually. Another thing here is to convert a PySpark data frame into a Pandas data frame. Why should we do that? First of all, because when you have small data sets, there is no point of actually using PySpark, which distributes the data across all the cluster nodes, which is good when you have a lot of data and you want to run things in parallel. But when you have a small data set, there is a lot of computational overhead. There is no reason to use a PySpark data frame. It's better to use Pandas, which is it only uses the driver node because it doesn't read distributed data, right? Pandas runs only on a single node. So also you can use many libraries that we have in Pandas that do not exist in PySpark. This is another reason. Now, how do you convert PySpark DataFrame to Pandas DataFrame? It's pretty simple. You use the PySpark DataFrame dot to Pandas, and that's it, pretty much. And this converts your PySpark DataFrame to Pandas DataFrame. As you can see, that's a typical Pandas DataFrame. And if you want to check the type, just run the type command, and you can see now it's a Pandas DataFrame. You want to improve the performance? Yeah, you can do that by using cache or persist for better performance. Cache and persist save the data frame in memory, making it faster for access in the subsequent actions. No need to re-execute the same transformations as it has already been cached and it is available. So it comes in handy when you want to save data in memory and you don't want to re-execute the same transformations in order, and so you want to save time, right, and space. And you can do that by using df with schema.cache. It's pretty simple. And then to the next example, this is how we can rename a column in a PySpark data frame. Now this is very typical. Imagine you have a relational table and you are using SQL. So here we are going to see the equivalent of the SQL functions, SQL commands that do that. So to provide an alias in SQL, you select the column as and you provide the alias. Here you can do that by using with column rename. So the data frame dot with column rename, you select the column that you want to rename and then you select the column name that you want. So if we do that and display the data frame, as you can see here now, instead of city, it's town. Pretty easy, right? Let's see the lit command. So here what we have to do is actually import the SQL functions from the library. So import PySpark.sql.functions as f, pretty standard. And the lit function actually is to assign a constant value into a column. And here what we can do is actually select everything and also add a new column with a constant value, so with a constant value of 1. And we can provide an alias for that column, which would be lit_value. Let's do that and see what we get. Here, as you can see, a new column was created with a constant value. Now be careful, because if we run this again, it will add one more column with this constant value. As you can see now, we have two columns with the same column name. You need to be careful of that, right? Another thing we want to do is actually use casting. Okay, so let's run the cell and see the changes in the schema. As you can see, we can use with column here to create a new column. It's pretty typical to use with column to create a new column. We get the age column and we cast it as a string from an integer. So let's run this. As you can see now, it's of type string. Again, here, when we want to create a new column, we use with column, the data frame dot with column. And here, let's say we specify a column that doesn't exist, new age column, for example, and it's based on another column in the data frame. Remember, usually you want to use a column, you want to create a column based on another column, and after performing some transformations here, we select the age column and we subtract 1 and we create a new column called new age column. So let's do that and see what we get. We get the new age column. As you can see here, it's we subtracted one from the H column here. Pretty easy, right? If you want to create a new constant column, again, you can use with column and the lit function. And let's create a new column called country, and you can see USA, that's a constant. Easy. And now here is when we join tables. Let's load the second CSV file. So let's load that. The same configuration as before. The second data frame, as you can see, it has an ID column, occupation column, and a salary. Now, how can we join those two data frames? Because one data frame, the first data frame has an ID column, an age column, a town column, and a country column. And here we have ID, occupation, and salary. If we join those two, we can join and select at the same time, but we can also provide an alias. So that's why I did it all in one go. You can use, you can join data frames based on dot join, as you can see here. So data frame one dot join, you provide the second data frame. You have to specify the keys that the join will be based on, right? And here is the ID column, the only common column that we have in both data frames. It will be an inner join. You can use left join, outer join, etc., etc. And then you can select the columns that you want. From data frame 1, we select the ID column. From data frame 1, again, we select the age. And from data frame 2, we select the salary. And you can use the F functions to round the salary. The salaries are already rounded, but just to show you an example. And here, as you can see, when we use a function, an SQL function here, how can we provide an alias to this function, to this new column? Using the with column renamed again. But here we need to provide the name, the output name, when it, as it comes when we apply the SQL function, and it comes like that. So that would be the column name of this new column here. So using this column name, the old column name, then we define the new column name, and then we sort based on a descending order based on the salary, using again the SQL functions dot descending. And then we show the data frame. Let's see what we get. And we get this new data frame here after the joins. So let's say that we have a big table, and then we have a small table to use for a lookup table to use for lookup activities, which is a pretty common scenario in ETL processes. So how can we improve the performance in those kind of joins, the lookup joins? We can use the broadcast join. Now, broadcast, remember, is that we broadcast a small data set across the worker nodes, so we don't have to shuffle this small data set around in order to perform the join. So this is how we can improve the data. PySpark splits the data into different nodes for parallel processing when you have two data frames. The data from both are distributed across multiple nodes in the cluster. So when you perform a join, PySpark is required to shuffle the data. With broadcast join, we broadcast the smaller data frame to all the worker nodes that keep this data frame in memory, while the larger data frame is distributed across all the worker nodes. So we can perform a join without shuffling the data. How can we do this? Pretty easy. Here we join the first data frame using .join, and the second data frame, as you can see here, we have the second data frame, but we have to use the broadcast function from the SQL functions here. So f.broadcast, open bracket, we provide the second data frame, again, the keys that you will be joining those data frames, and perform a left outer join, and you select all the columns. Of course, here we have two small data sets, so a broadcast join doesn't make any sense, but this is how you perform broadcast join. Actually, lookup join if you wish, but with improved performance. So if we run this again, that would give you the results of a normal join. You won't notice anything on the outcome, but instead you just know that it's it's pretty handy when it comes to lookup activities. And here again, if you want to see, we perform the same join, but if you want to see the logical and physical plan, just type .explain extended true, and you will see the logical and physical plan, so you can evaluate the joins here. As you can see, we have the optimized logical plan, and we are using the broadcast hash join. Let's move to the aggregation part. As you can see, how can we use group by in our PySpark data frame. Again, we have to use a group by statement as always. We group by salary here, and we need to use .ag for the aggregation. For example, here we count star alias count, and we can see this is a pretty common group by activity. We can see the count here. As you can see, the people with this salary, we have 3 occurrences. The next group by is by occupation. We group by occupation, and then we use .ag, and we can perform multiple aggregations at the same time. Here we perform a max. We need to find the max salary, and we can provide an alias, as you can see, and the average salary, and then we provide an alias. And of course, we can use also a where clause, which is an alias for filter, as you will see in a bit. And we filter all the salaries that they are greater than 45. Let's run this, and it will give you this result here. And the same, we can do the same, but we can use .ag, and here we can pass a dictionary instead of the way that we did it here, right? That's another way of doing that, just passing a dictionary with the columns and the aggregations we want. Here we calculate the average salary and the count with column renamed. Again, this is how it's going to give you the average salary column. So that's why we want to rename it in one go. You can, of course, you can do that later. And we can use .filter, which is the same with the .where, same thing exactly, to filter the average salary. And then you can see here the results. As you can see now, the count is like that. So if you want to rename it, you can do it now after you have performed the aggregations and the filtering, or you can do it in one go using the with column renamed in one statement. Moving on, we have how to union data frames. It's pretty easy. Let's reload the same data frame from the testdata2.csv file. So we have this data frame here, and if you union those 2 data frames, what is going to happen is you can see we get duplicates, because that's not union distinct, that's union all. If you want union distinct, you have to use the distinct in the end after the union here. So we have data frame 1 dot union, data frame 2, and dot distinct to get the distinct values after the union. Pretty easy. Then we can define our own function. So UDF, right? Here we specify the typical convert to uppercase function. So that's Python. We define the uppercase function, we pass a string, and we convert the string into uppercase, and we return the results. How can we specify the user-defined function? How we can define it? By using the UDF from the SQL function. So f.udf and this is how we pass. That's the definition of the user defined function. So lambda for each item converted to uppercase, and the string format here is the type of the data type, the type of the data that we return from our uppercase function here. We return a string, that's why that's string type here. And that here we use the anonymous function because we are going to use this uppercase UDF within when we play around with the data frame. So for each row in the data frame, just perform this convert the text into uppercase. So here, when we have this data frame, we can create a new column, or we can select the previous an existing column, for example, occupation here, and convert the occupation into capital letters. So the occupation here, as you can see, is in lowercase. And here, if we let's run these cells here, and now what it's going to do is actually transform the string into uppercase. As you can see, the occupation now it's in capital letters. Perfect. That's how you define your own functions, but bear in mind this is an expensive operation. So if there is something, if there's a similar function that you can use from the SQL library, use that. Let's say you want to use the map operation that only exists in a resilient disability dataset and it doesn't exist in a data frame. How can you apply the map operation? Well, actually, you can convert a data frame to an RDD and use the map function here and then convert the RDD back to a PySpark data frame. So you have to define the schema here. Then you can convert the data frame into an RDD. As you can see now, it's the data frame was converted into a resilient disability dataset. And then we can apply the map function here. So df.rdd.map lambda, we pass the columns and the transformations we want. So for example, the first column, we want to multiply the first column by 2. The second column would remain the same, and the third column we want to apply 50. And this is the results that we get. As you can see, everything was multiplied by 2, and at the third column we added 50. Now this is still in an RDD format, and here we use spark.createDataFrame. We pass the RDD, we pass the schema, and this is how we can use the map function and functions that and operations that exist in an RDDs only in order to use them in data frames. So you convert a data frame into an RDD, you apply the transformations you want, and then you convert the RDD back to a data frame. This is it for today, guys. A quick introduction into PySpark DataFrames. I tried to include the most common PySpark functions that we normally use as data engineers. Obviously, there are plenty of other functions that you would need in order to create a pipeline, but hopefully I helped you a little bit with the basics. If you like the video, please click the like button, leave a comment and subscribe to the channel, and I will see you in the next one. Thank you.